Most people think scaling language models just means adding more parameters. But that's exactly why inference costs are skyrocketing. The real breakthrough isn't density, it's sparsity. Enter mixture of experts, or MoE. At its core, an MoE model doesn't activate every weight for every token. Instead, it splits the feed-forward layers into discrete expert subnetworks. When a token passes through, a lightweight router network evaluates its hidden state, computes logits for each expert, and routes the activation to only the top K, usually 2. Everything else stays completely dormant. That's how you scale to hundreds of billions of parameters, while keeping compute per token roughly constant. The routing mechanism is where the engineering gets interesting. Modern implementations use a learned gating network with a softmax over expert scores. But naive routing causes expert collapse, where a few experts hoard all the tokens, starving the rest and breaking gradient flow. To fix this, researchers add an auxiliary load balancing loss. This penalty term encourages uniform token distribution across experts during training, often combined with top K routing and straight-through estimators, so gradients can still flow through the discrete selection step. On the inference side, MoE models leverage expert parallelism. Each expert can live on a different GPU, and the router just broadcasts the token to the right device. Combined with KV cache optimization and speculative decoding, you get near-linear scaling of capability without the dense model's memory bottleneck. That's why every major architecture now ships with an MoE variant. If you want the math behind the auxiliary loss, how expert parallelism works with NCCL, or how MoE compares to dense distillation, drop a comment. I've linked the original papers and implementation notes in the description. Subscribe for more deep dives into the architecture behind the next wave of AI.